Okay, so my first question. What is that process which makes petrol? What is that process called? So I will only cover the topics that you guys told me in the group. So I'm going to just really rapidly skim through these first pages. So just tell me briefly, what is that process called which forms the petrol? Yes, Aisha, very good.
Fractional distillation.
Please speak loudly.
Fractional distillation.
Yes, very good. Please slow down the fan. Yes. No, not fractional distillation. No. Fractional distillation is the process which refines the petrol. I'm asking the process that forms, that makes the petrol. Fractional distillation, it is what refines it, what separates its parts. Okay, real quick. No, nobody knows. By the way, where is Zainab? Okay, so you guys don't know. So does that mean I have to cover this part as well in detail? Is that what it means? You don't know the process that forms the petrol?
The death and decaying of the fossil
Yes.
fuels.
Yes, very good. Decaying of, yes.
Fossil.
Yeah, please speak loudly. And don't mute yourself, right after you're done speaking, don't mute yourself. Yes?
The death and decaying of the fossil fuels.
Yes. Don't say decay of the fossil fuels. See, decay of the dead bodies, dead organisms, especially the marine creatures, the sea creatures, due to two processes. One is bacterial decomposition. The other is the pressure of the layer of mud above them. So pressure, high temperature, and bacterial decomposition together convert these dead organisms, the remains of these dead organisms, into what is called shale. It's a hydrocarbon mixture, transformed it into shale. Okay, what is shale? Shale is a mixture of hydrocarbons. It is a crude form of oil. Okay, remember, what is petrol? What do you understand when we say petrol? What comes into your mind? The car fuel, right? That we put into the cars. Yes, but what is it?
A mixture of hydrocarbons.
Very good. Yes, a mixture of hydrocarbons. So these hydrocarbons are same, different? How are they different?
They have different boiling point.
Boiling point.
Okay, they have different boiling point. And why is that? Why do they have different boiling points?
Difference in the carbon chain.
Yes, different in the carbon chain, like what? Arrangement or what?
The number of the carbon.
Yes, so say it. Yes, very good. Yes, so they differ in the number of carbon atoms that they have in their chains or backbones of chains. They may be branched, they may be unbranched, they may be saturated, they may be unsaturated, so on and so forth. Okay. So when we get petrol from underground, it's a mixture of hydrocarbons, and there are many different types of hydrocarbons. Now, we don't want all of them, and all of them have different uses. The smaller number of carbon chains, starting from carbon 2 to carbon 8, not 2, but yeah, around 8, 4 to 8, maybe 8 to and then 10, around this range, we use these hydrocarbons as fuels. Okay. Then even within fuels, there are different types of fuels. Okay, like you must have heard diesel, and then you have petrol, and then there are other categories. Okay, I'm not going to go into the details, but they all differ in the number of carbon atoms. So because they have different uses, we are interested in separating them. Okay, and that's why they use this fractional distillation to separate them, and we make use of their difference, the difference in their boiling points, and then we separate them. Okay, well, fractional distillation is the separation of different components of a mixture based upon the difference in their boiling point. So you guys know fractional distillation. I'm not going to go into the details, right? We have done it many times. So, what happened? Oh. Hello, am I still in the meeting?
Yes,
Oh, okay.
Miss.
Okay, sorry. Okay, so let's directly jump onto, now with that background knowledge, let's jump onto the catalytic cracking. Okay, now why do we need catalytic cracking? First of all, what is it? What is it? Any ideas? Yes, Hala, very good.
It is the breakdown of large unreactive alkanes
Yes,
to alkenes, which are reactive by using enzyme and high temperatures.
yes. Um, yeah, but not because they are unreactive or reactive, not because of that. Yes, we do break those bigger, longer hydrocarbons into smaller ones, but the reason why we do that is this. On this page, maybe zoom out. Yeah, this page, what page number is this? 279. Okay, now what are they saying in this picture? That as the number of carbon atoms increases, their demand decreases because their value as a fuel decreases. Okay, why does the value as fuel decrease? Maybe it has to do with reaction. Yeah, maybe you are right. But yes, it has to do with how much energy they are releasing when they're undergoing combustion. So if they're releasing more energy when they're undergoing combustion, that means they are good fuels. Okay, and if they are releasing less energy, then that means they are not good fuels, and therefore they might be used for something else, like lubrication or as waxes, or there are many other different uses. But the fuel is of the utmost demand. Okay, we need fuel. The Western countries need fuel because they are all cold and they have central heating systems and everything. So that all runs with gas, petrol. So for that they need. So that's why fuel, by the way, the highest quality, highest demand fuel is this petrol, which is carbon 8. It has carbon 8. I'm sorry for the low resolution of picture. The resolution is not good. Yeah. No, I don't want to zoom in. I want, yeah, improved resolution. Yes. So it's carbon 8, also called octane. You must have heard this name on the petrol stations, octane. Octane is this high quality petrol, C8. Okay. Now what makes a fuel high quality, low quality? We will not go too much in detail, but yeah, they have touched upon it. Okay. So because the smaller chain hydrocarbons are good fuels and therefore in high demands, the long chain hydrocarbons are in less demand, but they are being supplied at the same rate. They are being supplied in the same amount, but the demand is more of smaller ones compared to bigger ones. So they thought, instead of wasting these high hydrocarbon chains, and because petrol is so expensive, why not break these big hydrocarbon chains into the size that we want, right? Why not do that? And so that's why they came up with this process of cracking. Okay, so yes, you are right. Cracking is the breaking of bigger hydrocarbons into smaller ones, and then alkenes is a byproduct. It's not what we want. It's we want smaller hydrocarbons as fuel, but then alkene is a byproduct. We get it, whether we want it or not. Now, since we have it, so I mean, we have it in so much abundant quantity because whenever we crack, we get alkenes, then why not do something with this instead of wasting it? Why not make use of it? And so they make use of this alkene for different purposes. Okay, alkene is used for different purposes. One of them is polymerization, right? So yes, so for this process, they do need high temperature. Why is high temperature required? Because we are breaking, right? We are breaking the bonds. So it's endothermic. It will require energy. So this was a big hydrocarbon, decane, 10 hydrocarbons. It broke down into C8 octane and 1 ethene. So this is what was desired, but then we got this as well. Okay, now you can see that this alkene has a lower molecular mass because it has only 2 carbon atoms. And remember, low molecular mass means very low boiling points, right? Am I right? Yes, very low boiling point. So this will exist as a gas. So in order to condense it, we will need extremely low temperatures. Okay, so, and then it's not, and remember, this process is like sort of random a little bit. Like you cannot decide how many carbon atoms you can get. I don't know, not that they have mentioned it in this chapter, but I don't think it can be that tightly controlled. Like you can have 7 carbon atoms, you can have 6, you can have 8, you can have 9, you can have 10, so around a roundabout. Okay, that's why they have this fractional distillation. If you want pure octane, then you will get a mixture because you cannot decide which bond will break or where. You cannot decide that. So what carbon atoms you get in your product will depend upon which bond broke. You understand that, right? Now, if, for example, this bond breaks, then you will get hexene and then butene. That's what you might get, okay, if this bond breaks. So yes, but1ene is also one of the products, okay? And then propene, you can also get propene. So the bond can break here. You understand? So we cannot decide which bond will break. So it depends upon which bond break, that will decide what products you get. Okay. Okay. Okay, that's that. Now they're talking about that when we get these alkenes, what do we do with these alkenes? So as I told you, they can be used for polymerization. So with that, and yes, it is a catalyzed, that's why we call it catalytic cracking, because it requires a catalyst. And which catalysts are used? Silica, alumina, zeolites, and the temperature should be around 500 degrees Celsius. Okay, because this is an endothermic reaction because you are breaking a bond. Okay. Then what do we use the alkenes for? Especially the ethene? Ethene is the most common alkene which is produced. What do we do with it? These are the different uses of ethene. These are the different uses of ethene. We can, now we did the reactions of alkenes, right? In the previous chapter, chapter 10. So the same thing, okay? Bring from that chapter, remember from that chapter, ethene can react with steam to form ethanol. Remember, alkenes can react with water to form alcohol. And then many ethenes will undergo polymerization to form polyethene. We are going to discuss polymerization in a bit. Ethene can react with chlorine. This is substitution, addition reaction. This is addition reaction when halogen is added. The double bond breaks. Remember? This is ethene. And so chlorine molecule reacts with it, which is a diatomic molecule. And so this breaks. So you get this, right? So this is addition reaction. What happened is that this bond broke, and so each of the carbon atoms then bonded with each of the chlorine atoms. So this is called chloroethene. Okay, this is chloroethene. You can call it 1,2-dichloroethene, or sometimes only one chlorine is added. So you can just call it chloroethene if there are two, 1,2-dichloroethene. Okay. Then ethene reacts with benzene and to form phenylethene. Now, by the way, this benzene you have not done, and I don't think it is, you don't have to go into details of benzene. It's a complicated molecule. We haven't done it, but just remember that it reacts with benzene to form phenylethene. By the way, I don't like memorizing without understanding. But yeah, if you want to know more about benzene, then well, if you want to know more, then you can go ahead if you have time. You can Google search but I think knowing this much is enough for now for IGCSE. Okay, so these are the different reactions. So this chloroethene, many chloroethenes can join together to form polychloroethene. You know, many chloroethene will join together. No, sorry. So they will form polychloroethene. This is a polymer. Okay, we are going to now start polymerization after this. So okay, and then this cracking of a long chain alkene in the laboratory. So this is the laboratory setup. They have paraffin soaked into absorbent wool. Now, paraffin is also one of the components of petrol. Okay, I don't remember how many carbon atoms it has, but again, it is undergoing heat. And then this is a catalyst. Broken porcelain or aluminum oxide granules, they are catalysts. Now, what do catalysts do? They just make the reactants react faster. Okay, they don't participate themselves. They just make the reactants come into close contact with each other so that they can interact with each other faster and result in the product. Okay, here it's bond breaking going on. So maybe they are assisting in the breaking of that bond. And so we have like two products. One is alkene, the other is shorter hydrocarbon chain, right? The shorter hydrocarbon chain, since it has a relatively greater molecular weight and mass compared to alkene, therefore it can condense easily, passing through the, in this test tube, which is in the cold water bath. That means the test tube is colder compared to this test tube, because this test tube was being warmed. So it will condense here, and so you will have this small chain hydrocarbon collected in this test tube. Now ethene, because it has lower molecular weight and it will be harder to condense it, this temperature alone is not enough to condense ethene. It requires greater cooling. This is not enough because the molecule is too small. You cannot bring the molecules closer together. The smaller the molecules are, the farther away they tend to go from each other. So you'll have to cool them down a lot to bring them together in the liquid form. So since it stays in the gas state, it passes through this delivery tube and here, and because it is less dense than water, and it is not soluble in water because it's non-polar. It's non-polar. By the way, all these molecules are non-polar until they have a polar functional group. Otherwise, simple hydrocarbons are non-polar. Non-polar meaning not soluble in water. So because it is not soluble in water, It won't dissolve in water, and it will, and because it is less dense than water, it will be collected above the level of water. Okay, so this is the laboratory setup. Any questions so far? Please feel free to ask. Okay.
Miss,
Yes. Yes.
can you tell the laboratory setup again? I didn't understand fully.
What did you not understand?
The whole laboratory setup.
Okay, what did you not understand? Can you start explaining? See, this is paraffin, right? We are heating it. Why? Because we want to break a bond, right? So it's endothermic, we need to warm, right? And catalyst is assisting. You know what a catalyst is, right? You know the functions of catalyst, right? And then you have two products, alkenes and the shorter hydrocarbon chain. The shorter hydrocarbon chain condenses in this cold temperature, but because ethene is very small, it requires more cooling. It won't condense. It will stay in the form of gas. It will pass through this delivery tube. It won't dissolve in water because it's not soluble. It's less dense than water, and it will rise up the water and be collected in the test tube, right?
Oh, okay. Thank you, Miss.
You're most welcome. Okay, now let's jump on to polymerization. Addition, polymerization. Now, just excuse me. Okay, as the name suggests, addition polymerization. This is simple addition. Okay, this is simple addition. The reason why we are calling it simple addition, you will understand when we will do kind of condensation polymerization. So to differentiate from condensation and other types of polymerization, we name each type of polymerization. So this is addition. Addition meaning it's simple addition. And for addition polymerization, you need to have a double bond. You need to have a double bond. Okay. For example, let's do this ethene. This is the simplest monomer. Okay, what is a monomer? First of all, okay, what is a polymer and what are macromolecules? Yes, first you should know these terms, and then, okay, you wanna tell me what monomers and polymers are? What is a monomer?
Miss, there are small molecule, many small molecules that join together to make a polymer.
Very good, very good. And then what are polymers? Yes.
Polymers are joined by the monomers.
Yeah, many monomers join together to form polymers. Can you give me my necklace? That necklace? Yeah. Yes. Okay. Now, and what is a macromolecule?
A really big molecule?
Yes. Macro is the opposite of micro. Macro means really big molecules. You know, our hair is one molecule. One hair is one macromolecule. Why? Because it's protein. It's a big, long protein polymer. It's a big, long protein polymer. Our clothes are made up of fibers. Each fiber is a polymer. Okay, so these are macromolecules. Okay, so we can easily see macromolecules are easily visible. You don't need a microscope to see them. Okay, so think of this necklace. Each bead is a monomer. Each bead is a monomer, and whole thing is a polymer, like this. Okay. Okay. Now there are different ways of making polymers. So one is addition polymerization, for which you need carbon-carbon double bond, which is also called unsaturated hydrocarbon. So the simplest is ethene. Okay. So what are we doing? Nothing. Simple. this carbon-carbon double bond, okay? Again, so let's say there are 3 ethene molecules. Okay, I'm not writing HHH. You understand, right? These are all hydrogen atoms, okay? Because it will waste time. Okay, now hydrogen comes, addition, right? We are adding, right? When first by you're not adding hydrogen, just simple addition. So what's happening? These double carbons are breaking. One of the double carbon is breaking. Okay, so now one hand is available. One hand is available. One hand is available. One hand is available. You know, have you seen kids standing together, standing in a line or standing in a circle form and they're holding hands together? For example, this is one holding hand with another. Okay, holding hand with another. So these hands, so think of these as hands and they're holding hands with each other and they are forming big chain. So what will they form? Let me use a fresh page. Can I get a fresh page so that they understand in a better way? Okay. Okay, when this breaks, when this breaks, and when this breaks, they have extra hands then available. Okay, now what will they form? When they will join their hands, this is what they will form. Right? So the bond which broke went to bond with the neighboring ethene. The bond which broke went on to bond with the neighboring ethene. Okay, so what you came up with was a simple alkane. This is simple alkane depending on 1, 2, 3, 4, 5, 6. So this is a hexane. This is a hexane. Okay, but we also call it polyethene because it is made from ethene. Because it is made from ethene, it is also called polyethene. So the name polyethene shows that we got it by polymerization from ethene. Okay, poly, the word poly means many ethene molecules together. So it's called polyethene. Okay, mono means one, poly means many. So monomer, one molecule, polymer, many molecules in the form of a chain. Okay. Okay, so how do we represent monomers? So the monomer which reacted before reaction is represented this way in parentheses or brackets. Now, why do we write N here? Because there are many ethene molecules joining together to form a polyethene. We don't know a specific number. This number is variable. It varies. See, in polymers, there is no specific number. Only in case of proteins, which are found in our body, they have a specific number of amino acids. Like, for example, hemoglobin has a specific number of amino acids. But there are many polymers, but other than that, other polymers, they do not have any specific. Like, for example, hair. Some people have short hair, some people have long hair. So people who have long hair will have more proteins, will have more number of amino acids going into forming the polypeptide, that molecule. So it depends, fibers are of different length. Some fibers are long, some are short. So there is no specific. So that's why they have given it a variable. Okay, it depends how many ethene molecule you used. Okay. Then because ethene molecule is so small, it will tend to move far away. They will tend to move far away from each other because the molecules are so small. Therefore, you need to have high pressure to make sure that they join together. Because what do we want? We want them to join together in polymerization. So high pressure, we don't allow them to go too far. Because if they'll go too far, they won't interact with each other. So high pressure is important. Catalyst is important. It will increase the rate, and then again, you need to break the double bond. So you need to heat, right? Okay.
Miss, can I ask a question?
Yes.
Why is for monomers, why is the N written over there, and for polymers, the N is written at the bottom?
Yeah. So, well, I don't know why is it written at the bottom and why is it written at the left, but this means to say that this will continue n times. The chain is continuing n times. Like, for example, you saw here, I used 3 molecules, right, to show. So it gave me, you can say it gave me polyethene with 6 carbons. It gave me polyethene 6 carbons. So I could have written it this way. So this unit will be as many times as you have this. Sorry, for example, it is 3 in my case. So this will also be 3. Okay. But yeah, I don't know the reason. It's just, I think, convention that in the next to monomer, the N is written next to the monomer and and they write the variable at the right lower corner of the polymer. Okay. I think it's just a convention. It's just a rule that they follow. Okay. So that was a simple example. Now we have like propene. Now propene has 3 carbon atoms. Now, one very important point, if they give you a monomer like this, okay, and then they ask you to make its polymer, then I used to make that mistake, and many students make that mistake. It's a study tip. They have mentioned that mistake, and they are urging you not to make it. Can I have a okay. Okay, remember to keep the double bond carbons in the backbone. Okay, actually, the problem is that my laptop has this thing that it filters the sound that comes from sideways. And so my copy is on the side. So when I make a diagram, my mouth goes sideways and then you cannot hear me. And so it's difficult for me to draw any diagram. So where was the, can you hold this? Yes, this is better. Yes, this is better. Okay, so this is propene. Okay, so appreciate the fact that they, sorry, they made the 3rd carbon as a chain. They made the 3rd carbon as chain. You know why they did so? I'll tell you. So let's see. I will again make 3 molecules of propene. I will again make 3 molecules of propene to show you. Okay. Now this is addition, right? Addition polymerization. So the bond will break, the double bond will break, and they will have hands available to hold on to each other. Okay. This will result in this. So I am only showing the double bond carbon atoms, right? Okay, only the carbon atoms which were involved in double bonds. Even if it was butene, the branch would have been like this. The fourth carbon atom also would be shown as a branch, no matter how long the other carbon, the rest of the molecule is, it will be shown as a branch if you are showing polymerization in a diagram like this. You know why? Because it is only the double bond that will interact, that will react, that will undergo reaction. And so the backbone, the actual backbone of the molecule will be made of the carbon atoms which are involved in double bond only. The rest will be in the form of chains. Okay, remember this. So this resulting polypropene. Now this is polypropene. Propene, from propene you get polypropene. So so this molecule here, yeah, erase this. So two carbons from here, CH3, then two carbons from here, again CH3, then two carbons from here, CH3, and then fill them up with hydrogen atoms. Yeah. Fill them up with hydrogen atoms. Yes. Okay. So this is the propene, sorry. This is the propene. N number, this is polypropene. Okay. This was, so for example, 3, right? So this will also be 3. Okay. So I wanted to show you, what I wanted to show you was that you only draw the double bond carbon atoms as your backbone, as this is the backbone. The rest will be in the form of chain. Okay. Chain can be very long. It can be very, very long. Okay. Go on. It can go on. You can have hexene, heptene, so on and so forth, right? So only the double bond carbon atoms will form the backbone. The rest of the molecules will be dangling, hanging down. Okay, remember this. We used to make this mistake. I used to make that mistake. And so we get confused. Now, how to make the monomers hold hands together, because this big chain is coming in the way. How to make them hold hands together. Then we realize later, okay, so we're making this mistake because these should be in the form of chain, and you only show the functional group which is interacting, the functional group. In this case, it's a double bond, but there are other functional groups as well. So this was addition polymerization. Okay, now ethene can undergo, what was that called? Yes, substitution reaction, right? So chloroethene and then polychloroethene. So this is how you show, this is the equation of polymerization. N numbers of chloroethene will give you a polymer with N units, N repeating units. Each repeating unit is coming from one monomer. Okay. Tetrafluoroethene, tetra because there are 4 fluorine atoms which have replaced the hydrogen. Yeah, this is substitution, right? Hydrogen has been substituted by the halogen. So this is a substitution reaction. Okay. I mean, this is polymerization, but how did you get this? You got this by making ethene react with chlorine, substitution reaction. So you got this by making ethene react with fluorine, substitution reaction. So 2 molecules must be used. 1 molecule is diatomic, right? So 2 molecules. So there are 4 atoms, so must be 2 molecules. Okay, but this reaction is polymerization. So n numbers of monomers will give you a polymer with n numbers of repeating units, right? So this is called Polytetrafluoroethene Ptfe. This is Teflon, you know, non-stick pans. The non-stick pans, that black material, you know, the black surface, which is non-sticky, is material, tetrafluoroethene. It makes non-stick pans, but it is said to be carcinogenic. It causes cancer. It's related to causing cancer. Okay.
Miss, can I ask a question?
Yes, of course. Yes.
How will we know, like, what's the difference between the 2 diagrams of propene and ethene? Like, how will we know which one is propene and which one is ethene if the names were not given?
Okay. Yeah. Okay. That's a good question. That's a good question. So if, for example, you see this molecule, okay, you will look for a repeating pattern. Okay, they might give you clues in the question, like they might tell you that propene reacted. So you know if propene is reacting, so it must be polypropene. But if not, then even just by looking, you have to look for a repeating unit, repeating pattern. What unit is repeating itself? Can you see? This unit is repeating. This unit is repeating itself. So this must be polypropene. So this is the repeating unit. How many carbon atoms are in the repeating unit? 1, 2, 3. So must be propene. And if it's addition, you cannot see any other functional group. There must be double bonds. So ene. Okay, so propene, because there are 3 carbon atoms, so pro, and because there's no other functional group, so it must be the double bond. So ene comes from there. So propene. Okay. Similarly, and you cannot have from methane. Methane is simple 1 single carbon atom. Single carbon atom will not give you a polymer because it does not have the functional group. It does not have a double bond. So it cannot give you. So the simplest monomer that you can have is ethene, and then so on from there, ethene, propene, butene. But you cannot have methane. You cannot have methane. Okay. You cannot have polymethane or anything like that. Okay.
Oh, okay.
Is that okay? Now, some of the properties of addition polymers. All polymers are long chain molecules made by joining together a large number of monomer molecules. Involves monomer molecules. Either I think we have done this during addition. Okay, we have done all of these. Then from this table, yes, these uses are important. You might be asked, especially in structured questions. So you have to know them. Polyethylene is a plastic. You know, the plastic bags that we use for shopping, they are made up of polyethylene. They are polyethylene, and the bottles, and then polypropene gives you that harder plastic that is used to make boxes, hard plastic boxes and crates. Okay, and then polychloroethene is used for insulation pipes. And then this I told you, tetrafluoroethene is used for non-stick pans, non-stick frying pans. Then okay, this is the phenyl ethene or styrene, insulation packaging foam, you know, that packing material. Okay, this we haven't done, phenyl. It has to do with that same benzene that I was saying that we haven't done. It's a carbon ring that we haven't done. Okay, so yeah, I don't know why they mentioned something that we haven't done. Okay, let's give the molecular and structural formulae of ethene. I think you guys all know this, right? State what is meant by addition polymerization and give an equation for the formation of polyethene from ethene. So it's this same equation. This equation, polyethene from ethene. So make sure you write high pressure heat catalyst in your equations, right? And by the way, this is the molecular and structural formula of ethene. So ene, it has the suffix ene, which shows it has double bond. Okay, then we have this condensation. Now we go on to the second type of polymerization, which is condensation polymerization. Now, as the name suggests, condensation, a water molecule is released when monomers combine together. So the monomers have functional groups. How is it different from addition polymerization? Is that it does not have, the monomers don't have double bonds. Double bonds don't participate in the reaction, but rather the functional groups react. For example, let's take, they have given an example of nylon. Nylon is a man-made synthetic polymer. Okay, most of the polymers are made by Allah. Okay, I won't use the word nature. I don't like it. They have nature made, nature invented. No, Allah created, right? So, okay, so nylon is one polymer that was made industrially. I mean, man-made synthetic fiber. The word synthetic means man-made, not natural. Okay, so nylon is one example. So they make use of two types of monomers. Now, polymers, which are made up of only one or two types of monomers, they are called copolymers. Now, we have different types of polymers. Polymers are also of different types. Copolymer is that polymer which is made up of two different types of monomers. Okay, an example of a copolymer is nylon. And the two monomers that go to make it are diamine and dicarboxylic acid. Diamine and dicarboxylic acid. Wait a minute. Okay, so diamine and dicarboxylic acid. So this is amine. This functional group is called amine. Why do we call it diamine? Because each molecule has two amine groups on each side of the molecule. Now, you don't need to know the details of the rest of the molecule. Functional group is all you're concerned with. So you can represent the rest of the molecule in the form of a block. So that's a good thing. You don't have to worry about how many carbon or hydrogen atoms are in there. Just represent the rest of the molecule with the help of a block. But remember that different types of molecules should have different symbols. So if they're using shaded block here, they will use an empty block here, just so that you can differentiate. You can understand that these are two different types of monomers, not the same. Now, this is another type of monomer. Again, it has two functional groups, and this time they have carboxyl group. Carboxyl, C-O-O-H. C double bond O, C single bond O, and then H. Now, they go condensation reaction, meaning the OH from the carboxyl and hydrogen from the amine together forms H2O, water molecule, which is H2O. Okay, now when the water molecule comes out, these bonds are then available. These hands are available to hold on to each other. So they make a bond with each other. As a result, the linkage that we get is called an amide or a peptide link. I hope you can see it. If not, refer to your books. An amide or a peptide link. So remember this structure of a peptide link. What is it? C double bond O NH. CONH. This is an amide peptide link. Whenever you see this link, you should understand that two monomers reacted. One of them had a carboxyl group, the other had an amine group. This much should come into your mind, okay, whenever you see this peptide link. Also, this is the same link which is also found in polypeptides. What are polypeptides? Does anybody know? What are polypeptides?
Proteins.
Very good. Yes. The secondary form of the protein. Secondary form meaning? This form. Okay. So first you had individual beads. First you had beads. Okay. Then you connected those beads. They got connected. They form polymers. Right. And for example, I'm talking about polypeptides. So first you had the monomer in case of protein is very
Amino
good.
acid.
Yes, very good. Amino acid. So you have a lot of amino acids. Then they join together to form this, you can say a string or a polymer, polypeptide, which is called a polypeptide. This is called the secondary form. And then they then fold on to each other. They fold on to each other. This is called the tertiary form. And then further folding, this is called the quaternary form. And so you have the final protein, hemoglobin, for example. If you have seen the picture, Google Images, go on to Google Images, write down hemoglobin. So you will see something like this, So this is how the proteins are made. In proteins, these will be amino acids. They will be linked together by the same linkage called peptide link. Why? Because amino acids, same functional groups, react together again, same condensation reaction, water molecule is released, and they join together in the form of peptide or amide link. Amide linkage. Appreciate that in condensation polymerization, you have two products, the polymer and the molecule that got out, which was water in this case. Okay. So you have a table in which they are differentiating addition polymerization from condensation polymerization. They are comparing. Okay. One of the differences is that in addition polymerization, you only get the polymer, whereas in condensation polymerization, you get the polymer plus the other product. Okay. And then in the addition polymerization, you have double bonds, whereas in condensation polymerization, you have functional groups which are reacting together to release some molecule. Okay. Okay. Yes. Okay, so this was very interesting. You have YouTube video on this. If you are interested, you can go and watch. They are making nylon by reacting the two monomers together. So in the beak, one monomer. So what are the two monomers? Diamine and dicarboxyl, right? Diamine is this. Diamine is this 1,6-diamine hexane, and dicarboxyl is this decane dioyl dichloride and cyclohexane. Now, dioyl, don't go into that much detail. Dioyl is the same as dicarboxyl. Okay, this is dioyl means dicarboxyl. So can you see this is non-polar, so it will dissolve in an organic solvent. Organic solvent, because organic solvents are less dense, so that it will be at the top. And the other diamine is soluble in water. So because water aqueous solutions are denser, so it will settle at the bottom. Okay, second monomer dissolved in water, first monomer dissolved in an organic solvent. And at the interface, at this interface, they will react with each other and form polymers. And as they make polymers, they dip in a rod. The rod holds that polymer, and they take it, pull it out, and you can actually see a string, and they can wind it around this. It's very interesting. There's a YouTube video on this if you are interested. Okay, then we have, this is another type of condensation polymerization, but this time we are not making we are not making an amide link or peptide, but instead we are making the ester, because the linkages are ester. From chapter 10, do you remember which reaction produces ester? Does anybody know? From chapter 10.
Esterification.
Sorry? Yeah, okay, yes, esterification. So what are the two reactants? Which
Alcohol
two?
and carboxylic acid.
Very good. Very good. Jazakallah khairan. Alcohol and carboxyl acid. So that's exactly what's happening here. This is carboxyl. This is a carboxylic acid. Again, this is a dicarboxyl. And then this is an alcohol. OH, hydroxyl group, is the functional group of alcohols. Again, it has alcohol on both its sides, carboxyl on both its sides. So they interact with each other. You don't have anything to do with the rest of the molecule. Just represent them in the form of blocks. But remember, different blocks for different types of monomers. Water molecule will be released, condensation reaction, resulting in the form of this linkage between monomers called an ester link. Okay, what does an ester link look like? This is what it looks like. C double bond O with O of the neighboring monomer. So this thing together came here. This thing together came here. CO or here, CO, and then O of this, O of this. So this thing belonged to this, and this belonged to this. Okay, polyester. It's also called terylene. Okay, terylene and nylon are combined together to make shirts, to make clothes, synthetic fibers. Okay. Now here they are comparing addition polymerization with condensation polymerization. We have discussed them. We have discussed all the differences, but Sundus, help me with this. Help me. Okay. Yes. Okay. Yeah. So in monomers, usually many molecules of a single type of monomer. In condensation, you should have at least 2 types of monomers. In addition polymerization, where just 1 type of molecule will be enough. But there should be many of them, but type only 1. Here type at least 2. Here you have double bond, so unsaturated monomers. Okay, here functional group, reactive functional groups are required. In the backbone, you will show only double bond carbon atoms in addition polymerization. Here also, here you will show the molecules in the form of blocks, and you will only show the functional groups interacting together. Okay, you will just show monomers in the form of blocks. And you will also show the loss of a small molecule, which is usually water. Okay, each time, but it can be hydrogen, it can be other types of molecules, but usually water for you guys. Okay, nature of product, only a single product, the polymer. Here we have polymer plus that other small molecule. Now, another very important difference between them is that addition polymerization, in which the double bond breaks and they just hold hands together, is non-biodegradable. What does that mean? Huh? Loudly, loudly. Yeah.
It won't decay.
Right. It won't decay. Why? Because, you know, the bacteria that are found in our environment and, you know, under the ground, this is synthetic. This is man-made. Okay, it's not found in the nature. I mean, Allah did not create this. So, you know, when man makes something, it's always problematic, right? We are not good creators. We cannot create. So they created it. I mean, they tried to make it fine, but now there's problem. Now it won't decompose. Plastic does not decompose. It's a big problem, because ever since the first plastic was made, which was around 1950s, the plastic is only accumulating. It is not going anywhere. You're hoarding it up, you're piling it up, and it's piling it up in our landfills. So it's creating pollution. It's an environmental problem. Yeah, in the oceans, in the ocean beds, and everywhere. And they are unsightful. They look hideous. And so, you know, the reason behind it is that bacteria were made to decompose natural, or, you know, the polymers that Allah created. Because Allah trained the bacteria, designed the bacteria in such a way that they degrade these natural polymers, which he made. But bacteria, sorry to say, don't know how to deal with this. They don't have the enzymes. They don't have the machinery required to decompose these polymers. Okay, so they are non-biodegradable. So much so that even the acids cannot do anything. They are just lying there. So it's a problem. So they have tried to recycle them, they have tried to reuse them, but even recycling has its limitations. By the way, these condensation polymers that are produced by condensation, they are biodegradable, and they are also hydrolyzed by acids. Some of them are even hydrolyzed by just hot water, simple hot water. So they are more environmental friendly. They're more environmental friendly, and they don't cause pollution. So these days, there's a lot of research going on how to replace these artificial polymers with these condensation polymers, and how to use more condensation polymers, such as polyamide, maybe, or polyesters, instead of these polyethene. Okay. By the way, these plastic bottles, these hideous plastic bottles, they're all made of polyethylene terephthalate. You don't have to worry about what this means. You don't have to worry about it. Okay. Okay. So, yeah. And also these polymers that are made of condensation polymerization, they can even be degraded by a simple ultraviolet light. Okay, so that's a good thing. Then we have different types of plastics, and they use these symbols. These are, I don't think these are important from exam point of view. These are not important. Okay, but this is for recycling purposes, so that because there are different types of plastics, different types of polymers, and all of them need different recycling methods. So that's why it is important for the recycling factories to know what type of polymer they're dealing with. Okay, now they are discussing proteins. Okay, so there are different polymers inside our body. In fact, there are so many different types. Protein is a polymer, DNA, the nucleic acids, they are called polynucleotide. I wish I could show you Google images, but I didn't get the time to get the images. But you can go ahead and you can Google search the DNA molecule. I'm sure you must be knowing how it looks like. It's a double helix, and you can clearly see that it is a polypeptide. Many nucleic acids are joined together, just like you know, in the form of a string. Okay, which is helically shaped. And then you have carbohydrates. You have a glycogen, starch, and cellulose in plants. Okay, cellulose in plants. These are all polymers, natural polymers, I mean. Okay. So amino acids, so there are 20 different types of amino acids, which together form all the proteins in our body. All the proteins that are present in our body are all made up of different sequences of 20 different amino acids, 20. So think of it as we have 20 different letters, and then we have a lot of books made of those letters, right? So similarly, just like you have 23 letters, but you have lots and lots of books, right, in the world. So similarly, all of us are made up of only 20 different amino acids. Now, amongst these 20 different amino acids, a few of them we can get only from the diet. What do we mean by that? Like some amino acids, if we are deficient in certain amino acids, what the body does is that it rearranges the atoms to make those amino acids to overcome the deficiency. But not all the amino acids can be synthesized by our body that way. Some amino acids our body cannot make, but it requires them. It requires them, but it cannot make it. And so you need to eat them. There is no other way out. And some amino acids, if you don't eat, fine, the body will do something. The body will rearrange the atoms and will make an amino acid for you. And by the way, liver does that job. Liver does that job. But those amino acids, which it cannot make, but your body needs it, those are called essential amino acids. Those are called essential. The word essential means you gotta have it in your diet. Otherwise, you are in trouble. Essential amino acids, okay? There are some amino acids that we must obtain from our food. These are known as the essential amino acids because the body cannot compensate for their deficiency. That's why. Okay. Okay, the fats found in our body, they are also type of polymer made up of glycerol and fatty acids. Glycerol is a 3-carbon atom alcohol. It has 3 hydroxyl groups, 3 carbon atoms. This is glycerol. Okay, it reacts with 3 carboxyl acids. 3 carboxyl acids. Again, it's a condensation reaction. Water molecule is released. क्या हो गया? मैंने गलत कर दिया शायद. Oh, sorry. Okay, only hydrogen. Okay, I don't have the eraser right now. Can I have the eraser? Here, like this. Okay, only the hydrogen from carboxyl and OH from glycerol. And they make the ester linkage. They make the ester linkage. Remember, alcohol and carboxyl, when they react together, what do you get? Ester, right? So, and then they are long hydrocarbon chain. Okay, long hydrocarbon chain. Excuse my drawing, it's very rough. So what do you get as a result is this, right? This is the fat structure. This is the fat structure. Okay, so how do we get fat? From, these are called triglycerides. These are called triglyceride. Made up of the, how are they made? When the glycerol reacts with 3 carboxyl acids. When glycerol reacts with 3 carboxyl acids, so fatty acids are esters. This is a type of ester. This is called an ester linkage. This is an ester linkage. Okay, these are fats. This is triglyceride. Okay, this is important. And then they are also showing. So let's look at this. This is an amino acid. Okay, amino acids have, this is glycine. Glycine is an amino acid. It has carboxyl group on one end of the molecule It paused. Yeah. It has carboxyl group on one end of the molecule and the amino group at the other end of the molecule. All the amino acids are like that. They have carboxyl group on one end and amino group on the other end of the molecule. So it is the amino and the carboxyl, just like in nylon, but the difference was nylon had one diamine and one dicarboxyl. Here, the amino, both of them have one carboxyl, one amino, one carboxyl, one amino. That's the difference. But again, this will also go condensation reaction. A water molecule will be released and you will have a peptide linkage. So because there are two amino acids, it's called dipeptide. Di means two amino acids involved. Okay, this is called a dipeptide along with the water. Okay. Yeah, short polymers have up to 15 amino acids, and then bigger ones have 15 to 100. And if you have bigger than 100, then they are called proteins because they are so big, they need to be folded, like I showed you, like this, folded, okay, crumpled together. Okay, because to save space, because they need to be inside the cells. Cells are really small. Okay, as I told you, polymers that are natural and they are made of condensation, polymerization, they can be easily hydrolyzed. Hydrolyzed is the opposite of condensation. In condensation, a water molecule was being released. In hydrolysis, the water molecule will be added. Okay, a water molecule will be added. This bond will break here again. So let me make a water molecule. So this hydrogen will come here and make this amino group back again. This OH will come here, attach here, and make the carboxyl back again. So it's just the reversed. So this is a reversible reaction. Okay, but in order to increase its rate, to facilitate this reaction, they use acidified water because the protons in the acid, they ionize the water molecule and therefore they make this reaction easier and faster. Okay, so acid does not participate itself, but yes, it aids in the ionization of water, and maybe it provides a proton or hydrogen ion, which can help in the breakage of this bond. Okay, so this is called hydrolysis. Hydrolysis is the reverse of condensation. Okay. Then, so again, they are showing, so different amino acids are represented by different, by just blocks. Okay, they're just showing the functional groups which will take part in the reaction. Okay, and they are shaded a little differently. Okay, if you can make out in your book. So forward reaction is condensation. Hydrogen molecule is being removed or being released. Hydrogen in hydrolysis, water is being added. Okay, hydrolysis will cause this linkage to break into its constituent amino acids. Condensation will cause the amino acids to combine together to form a dipeptide, peptide linkage, right? Now, each individual amino acids can be recognized by which process? What process can we use to find out what amino acids there are for identification of amino acids?
Chromatography.
Very good. Yes. Yes, thank you. Because chromatography is a technique which is used to detect small amounts of substances in small samples, and due to their difference in their affinity for the paper and difference in their solubility in the solvent, with the help of chromatography, we can identify different amino acids. Because they are colorless, we need to use locating agents. Locating agents will give them color so that it's easier to identify them. Okay, then here they're talking about polysaccharides. Again, poly means a lot of molecules attached together to form macromolecules. We have 3 types of polysaccharides in our body. Animals have a glycogen, and then plants have a starch, and plants have cellulose. Okay, we don't have cellulose, we don't have starch, we have only glycogen. Starch and cellulose are found in the plants, right? Now, all these three polymers are polysaccharides. Saccharide means, the word saccharide means sugar, glucose. Mono, one sugar. We have different types of sugar monomers. Can you name a few? Yes, one is glucose, very good. Fructose, fructose is another one. Fructose is a pentagon, glucose is a hexagon. And then we have disaccharides. Disaccharides, two sugars together. Yes, sucrose is an example of, yes. Sucrose is an example of a disaccharide. So because it's a disaccharide, glucose has 6 carbon atoms, double of 6 is 12, so sucrose has 12. Okay, remember it like that. So this is 2 glucose molecules together. Okay. So again, they undergo condensation reaction. The water molecule, the functional groups react together. The rest of the molecule is represented by blocks. And you just show blocks joining each other via their linkages. This is called glycosidic link. This is called glycosidic linkage. Now, all starch, glycogen, and cellulose, all of them have glycosidic linkage. Remember, all proteins have peptide linkages or amide linkages because the functional group will stay the same. They only differ in this. What is inside these blocks, they only differ in this. The functional group will stay the same. If you have protein, all of them will have this peptide linkage. Boxes attached via peptide linkages. If it's a polysaccharide, you will have glycosidic linkages between the monomers. Okay, if you have polyesters, then you will have this ester linkage. So linkage, you will recognize the polymer with the linkage, with the help of the linkage. But then what is the difference between these three? If they have the same linkage, they are all saccharides, then what's the difference? The difference lies in their arrangement. Okay, the difference lies in their arrangement, but the basic functional linkage is the same. Only the arrangement of molecules is different. Okay, see, these three polymers differ in the way in which the glucose monomers units are linked together. Okay, this is also reversible. The reverse reaction will be called hydrolysis, which is aided by acid. Okay, they in individual sugars can also be identified with the help of chromatography. They are also colorless, so we will use locating agents. Okay, then we have identification tests for different groups of food molecules, such as, what is the identification test for starch? Who knows? Identification test for starch.
Iodine solution.
Right. It gives you what?
Blue color.
Right. Why does it form a blue-black color? Because starch with iodine makes a complex which is blue-black in color. Okay, just know this much. And okay, yeah, that's that. Yeah, and then they're talking about a balanced diet, and that's all. Okay, let's do these questions real quick. Name 2 natural condensation polymers.
Protein and
Proteins and
fats.
carbohydrates.
Right. Proteins and lipid, yeah, polysaccharides, polypeptides, yes, proteins and you can say starch, glycogen. Okay, what are the essential features of condensation polymerization? You can write any from this. These are all the features of condensation polymerization. You can write any from these. Okay, any from these. So they are made up of two monomers at least, and they have reactive functional groups reacting with each other, and then a molecule, and then a product is released along with the polymer. Another product is released, a byproduct. Name two artificial condensation polymers and specify the type of linkage present in each. Two artificial.
Terylene,
Sorry. Terylene, is that what you said?
yes,
Yes, yes, terylene, and another one?
Nylon.
Nylon. Okay, tell me their linkages. What linkage in terylene?
nylon is the amide linkage,
Very
and
good.
terylene is the ester linkage.
Very good. Good job. Okay. Draw schematic diagrams representing the formation of terylene and starch. Then you will show, okay. Yeah, this will be for terylene. Okay. You will show monomers. Remember to make different symbols, block, but just shade one and don't shade the other. Okay, carboxyl and hydroxyl. So remember, ester, for ester, you should have carboxyl and alcohol. You need carboxyl and alcohol. Okay, so carboxyl group and OH group. Okay, make them show water molecule out and then join them with the help of an ester linkage and the two different types of, and the monomer should alternate. One blank shaded, like that. I used to enjoy organic chemistry. For some reason, it was better than physical. It was better than inorganic chemistry, at least. Okay, the nylon is a synthetic macromolecule which is held together by the same linkage as protein molecule. Yes, and that linkage is?
Amide or peptide linkage.
Yes, very good. Amide or peptide linkage. Draw a diagram of the structure of nylon. So peptide linkage दिखाएंगे और दो different type के डब्बे दिखाएंगे. ठीक है? Different type के डब्बे with peptide linkages in between them. No big deal. And also show the water molecule. For each linkage, okay, another thing. How many numbers of water molecules? Same number as the number of linkages. So there are 3 linkages, 3 water molecules. Because each linkage is formed by release of 1 water molecule. So the water molecule will be the same as the number of linkages. Okay, that's another point to remember. Okay. Then give a major difference between the structure of nylon and of a protein. I discussed it. Let's see who remembers.
Nylon is made up of 2 monomers and protein are made up of many different amino acids.
Very good. Very good. Another, that
The monomer of protein, the amino acids, each amino acid contain both the functional group, the carboxyl and the amide.
very good. Yes, yes, very good. And in nylon, we have, in nylon, the monomers are diamine and dicarboxyl, right? Each monomer, one monomer has 2 amine groups and the other monomer has 2 carboxyl groups. How can proteins be chemically broken back down to amino acids?
Hydrolysis.
Yes, hydrolysis in acidified water. Okay. Okay, so with this, we have come to the end of this chapter. Is there any question? I don't know if we don't have time for this. I did not go through these questions. I didn't get time. Do you want any help with any of the questions?
No, miss.
Okay. Okay, then best of luck. Okay, is there any question?
No, miss.
Okay, okay, then may Allah help you. May Allah make all the exams easy for you. Okay. Okay, assalamu alaikum. Warahmatullahi wabarakatuh.
Thank you, Miss. Allah Hafiz.
Okay, you're most welcome. Allah Hafiz, Allah Hafiz. Allah Hafiz, you're welcome.